Hey, ladies and gentlemen, welcome back to Calculus. I apologize that I'm not with you today. You have a sub, and it's going to be a great day. Uh, yeah, I need us to pay attention, help each other, and work hard. Here's where we're going to start, though, if you don't mind. Pull out your Chromebooks, and if you could and would, log into Canvas, and you should find a quick ACT review quiz here. I'd like you to take 5-10 minutes and see what you can answer here. Should be 5 questions to answer. Yeah, with a calculator, see what you can answer on your own. Good practice for the ACT. Sub, you want to pause the video? That'd be awesome. Okay, hopefully you did well with that. Here are the solutions from yesterday. So let's pull out yesterday's assignment. We have looked at the area under a curve. We use some methods called just counting squares and stuff and finding what the area ends up being. As you take a look up here, pull them out. And again, the sub can pause the video. And if we need to have some discussion with our classmates, let's have some discussions. But if you take a look here, again, I know the order a little bit. Sorry the way I made this up and down here. But on number 1, A and B, again, these are approximations again. So are you getting close on part A to 30.8? Again, it doesn't have to be exactly 30.8 because chances are you're going to count a little bit differently. And same way on B, 41.8. This is what someone at one time had said what the answer should be. But again, you could have different answers there. Sine, as I go from A again, I can't even remember where I'm going from, but part A I should get roughly 2. And then B, it ends up being exactly half as much, so that's why it's 1. So again, are you close to 2, close to 1? Kind of within the ballpark there. Number 3, take a look at your answers there. They got 680 feet. And so as they counted squares, each square ends up being 5 by 20 units long. So they're multiplying by 100. Because 5 by 20 is 100. So they're saying there's 6.8 squares roughly times 100. They're getting 680 feet. Are you close to 680? Why are the labels feet, though? Those are questions we should ask. 4 is kind of a tough question, and maybe we'll see. Maybe at the end of the video, we can come back to this, and this might be worth seeing, or I can answer it in class tomorrow. But 4, sorry, the answers look like this. My range goes from 0 to 32.566. I can share with you how we can find that, but if I set my domain to be from 0 to 10, I'm looking at this graph. It keeps increasing. When I get to 10, the max of it ends up being, my range goes up to 32.5. As I work backwards, do some things we did in pre-calculus, I find that I get 8.7 seconds for B. They want us to find the rate of change, or sorry, counting squares on C, and roughly the area under my curve ends up being 150 feet. I didn't highlight that one, sorry. D, we're doing what we did earlier. I'm finding a rate of change, so that's a derivative. I'm estimating a derivative. I'm finding the slope. So they used a little different method here to find slope, but I need to plug in 2 points really close to my point is what I would do. Plug it in the equation, use the equation method. I should get something close to 3.1. Notice my labels, though. Because my y value is feet per second, my x value is seconds, I get feet per second, or that's also known feet per second squared, which is what we call in physics, we call that an acceleration. So another way to write this would be feet per second squared. On the back side, what's a derivative? Again, finding the derivative. Again, don't look at their work. We did it the equation way, plug in my points, plug in something really close to it, find the slope between those two. Do I get something close to 3.4? 6 should be exactly -7 because my function's aligned. So when I plug in my point and plug something really close to that point in, it's going to be -7 because my slope's always -7 there. And then on number 7 here too, you're going to find the total amount of travels is 7.1. Part of it's positive area, so you're going above the x-axis, so I get 11.4 roughly amount of area above the axis, but then I'm also getting some area below the axis, which is 4.3. I take the positive area minus the negative area essentially, and I'm getting the total amount is 7.1. We can talk about these maybe, I guess, on Tuesday or Monday when I'm back. Yeah, I'm going to keep rolling along so you have some time to work and do some things. Now, today we're going to spend a little bit of time looking at definite integrals. And so this is going to be kind of the same thing we did yesterday. And again, we're just trying to estimate this. And so I'm looking at estimations for this because we don't know how to do this exactly. But I want us to understand the idea of all this. Again, what is a definite integral? We're going to do it actually by looking at trapezoids. Because trapezoids work really, really well. Define areas under our curves, and I'll show you kind of why here in a moment of why that might be. So today, again, let's pull out our notes. Let's take some notes. Again, if the sub needs to pause the video, write stuff down, try these things. Again, I know you can just watch and see, but again, until you do it, you really don't know what we're doing until we try it ourselves. So I encourage you as we work, try things. Maybe you get it wrong. That's all right. Fix it. Learn from it. But keep moving forward. Now, this I have somewhere here. Mr. Roy, sorry. Forgive me. Not there. Here. I know I showed you, I think probably yesterday, something very similar to this. We want to find the area under a curve. And as I look between these 2 points, between A and B, what I have through this little applet program is I can actually take like some rectangles, and I can say between A and B, this is how much area it is. And we're going to talk later on, they're going to call these lower and upper sum rectangles. Maybe I'll just put them together here, is what it looks like. But I have 3 rectangles between A and B. And this has so much area, and it shows right here, the area is 1.4. This is not a good estimation of how much area is under the curve between A and B. What makes it better is that as I go, I can have more and more and more of these rectangles. And as you see, these rectangles get smaller, but actually my area, they start to fit the curve better. And what we're going to do as time goes on, we get into what is a definite integral. It's the area under my curve. If I want to find the exact area in the curve, what I really want to do is I want to add up more and more rectangles is what we're going to use. And the more I can have, aka an infinite amount that I can have, I'm going to get the exact area under my curve. And so later on, we're going to do the impossible. We're going to add up infinite amount of rectangles, and we're going to find the exact area under our curve and do other things with it, where it might be. Now, again, the more I have, the better it fits, right? Again, with just a few rectangles, not a good fit for this curve. Now, the one thing I'll point out, though, is if I look at trapezoids, and that's what we're going to look at today, trapezoids work way better, right? Again, if I just had one trapezoid, that one trapezoid does not fit my curve very well at all. But as I go to just say, maybe, no, sorry, a little sensitive here. If I go to 2 trapezoids, that's a little better. 3 trapezoids, even better. 4 trapezoids, or 5 trapezoids. Do you see how well this fits just with 5 trapezoids? Like, trapezoids fit my curve way better because of how they're designed and how they're made. And again, it doesn't matter how many, again, like rectangles, the more and more that I have, the faster it ends up fitting my area under my curve and the better that it fits. And so today we're going to look at, again, later on in calculus, we're actually going to use rectangles because I'm going to argue rectangles are way easier to use, and it doesn't matter as long as I have an infinite amount of them, it's going to fit my curve perfectly. But today for estimating, trapezoids work really well as a way to estimate the area under a curve. And so we're going to talk about using trapezoids to do that. And so hopefully the visual gives you a little idea of what we are doing, where we're at. So I wanted to show you that. And so let's talk about trapezoids. I know some of you just took the ACT the other day, and so you probably talked a little bit about this. Maybe this popped up on the ACT. Wish I remember this formula, Mr. Roy. But if I have a trapezoid, by definition, it's a quadrilateral where I have 2 sides that are parallel to each other. We call this one a base, the other one a base. It has a height. The height, though, here's what's key about my height, though. The height is always perpendicular to my bases. The formula to finding one area of a trapezoid looks kind of like this. It looks like I have, I don't know if you remember it though, it's actually just based upon a rectangle. But if I put these together, it looks like this. It's 1/2 the height, and then base 1 plus base 2. And so this is a formula, how we find the area of one trapezoid. Looks like this. Now, if I go again back, I don't know if I can do this. Can I do this? I'm sorry, nope, don't want to see that. I need to go back. I have too many tabs here. If I go back to this though again, if you look carefully at these trapezoids here, each trapezoid here, I don't know, can you see this very well? Each trapezoid here, the bases are actually going up and down. So this base right here maybe is one base. This is another base. I'll call this base 1, this base 2. The height actually is this piece that goes side to side. This height right here, that's the height. So the change in my x value ends up being my height. So my trapezoids are sitting sideways here, not sitting like they normally do when you look here in geometry where they sit like this. But a lot of times in a moment here, we're going to see them. They're going to look like this, or maybe this is my trapezoid, where this is one base, this is another base. So base 1, base 2. Again, this distance between here and here is going to be my height. You follow me there? And so as I have my trapezoid, it's going to be sitting sideways instead of the other way. Here's what I'm going to have you do. If in your notes, take a moment here. We're going to use the same function. This is going to be kind of our go-to, and I want you to see and compare a little bit. So we're going to talk about some ways we can do this and ways to streamline and make this a little bit quicker for us. But here's what I'd like you to do. I want you to graph this function, fx equals x squared. This is just a parabola, right? Again, I'm only looking at the right side of my parabola, x squared, starting at the origin. Again, my picture, I kind of zoomed out using GeoGebra is what I did. But here's what I want us to do. I want us to estimate the definite integral, aka what that's saying is I want us to estimate the area under the curve between 1 and 5. And I want us to do what we did yesterday. So this is yesterday. Go back. Let's do what we did yesterday, counting squares. I just want you to see counting squares works. Trapezoids are way better. So if I start at 1, 1's right here. I want to go all the way to 5, right here. All I want to do now is find that area under my curve, count some squares. So if I were to do this, and again, maybe the sub needs a pause it so they can draw this and try it themselves. If I'm doing this, I'm going, okay, I have 1 full squared here. This is pretty much a full square there. I don't know. What else would I be looking at? This right here, maybe this, and then this little piece together, that makes 3 full squares. Gosh. This one right here, like this little piece, plus this little piece right here, maybe that's 4 full squares. And then, I don't know, what are you thinking here? I have this little bit right here. What do I want? I don't know what I want to say here. Maybe this is how much of a square right here? What do you want to go with? I'm kind of at a loss here what this should be. Maybe I'll say this is like 0.25 of a square. I don't know. So if I had to say my estimate, counting squares, I'm saying I have 4.25 squares here. That's my guess. Now, based on yesterday, though, that's not my area, though. My area under my curve, though, would actually be this. How big is each square? So if I look at my graph, the way I drew my graph, each one of these is 1 unit over. I'm going 1 unit over, but then I'm going up 10 units this way. So 1 square actually equals how much? It actually equals 10 units squared. Does that make sense? So 1 square equals 10 units squared. So if I take this answer times 10, this is actually my approximation for the area under the curve. I would actually say for my answer, I have roughly 42.5 units squared. That's my estimation by counting squares. I'm saying I have roughly 4.25 squares. Each square is 10 units squared. And so if I multiply each of those squares by 10 units squared, I'm getting roughly 42.5 units squared. That's how much area is under my curve, just counting squares. And counting squares works really, really well. but there's better ways to do it. Let's fast forward. Same question, same problem, except for new method. Let's do this now using some geometry. Let's estimate the definite integral, again, aka the area under my curve, from, again, 1 to 5. But I want to use now what's different. I want to use 4 trapezoids. So I'm going to be going from 1 to 5. And I want to break this down into trapezoids here and estimate how much area is under my curve with trapezoids. So here's, first of all, what I need to figure out to do. If I want to do this in 4 trapezoids, again, notice I'm not doing 100 of them, but just 4 of them. I need to figure out how to subdivide this into equal pieces. We call this in a moment, I'm going to call this the change of x, is what I'm going to call this. But if I want to figure out where to put my trapezoids, I know some of you are just going to say, well, it's easy, Mr. Roy, you just draw each unit, you're going to draw a line, and that's going to subdivide it. But if you want to find the change in x, where this might be, it's always going to look like this. It's going to be this formula of b minus a divided by the number of things I want. And so when I say b minus a, I'm going from b is this is my b, that's 5. My a is my starting point, 1. I'm saying the distance between 5 and 1 is 4, so 5 minus 1 is 4. N is my number of trapezoids I want, so this is the number of trapezoids I want, is 4. What is my change of x going to be if I want to have 4 equal spacings? It's going to be 5 minus 1, 4, divided by 4. This is going to be 1. My change of x is going to be 1. So if I'm starting at 1, if I go 1 unit over, I'm going to be at 2. Go 1 unit over, I'm at 3. 1 unit over, I'm at 4. 1 unit over, I'm at 5. These are going to make trapezoids. So if I draw this, I don't know if you see this, this is what this trapezoid is going to look like. That's one trapezoid. If I draw this one, connect the dots. This is my second trapezoid. This is going to be my third trapezoid. This is going to be my fourth trapezoid. You see these 4 trapezoids here. But I found the distance between them, this change of x, to be 1 by doing and using this formula right here of take your upper bound b minus your lower bound a, divide by the number of things you want to subdivide it into, and that'll always tell you how far to move over. In this case, move over 1 unit, and you get 4 equally spaced trapezoids in there. Does that make sense? So I need to first figure that out, subdivide this into where it might be. Now, secondly, then, I'm just going to do some brute force now. I have 4 trapezoids here. I want to find the area of all 4 of these. So the area of my first trapezoid, I'll call it A1, looks like this. So again, formula for a trapezoid is 1/2 height base 1 plus base 2. Well, here's what we got to plug in. So this is the area of any trapezoid. Good. Let's plug in the first trapezoid. Well, first trapezoid, I have 1/2. But then what's my height though? So if I look at this trapezoid, and again, it's a little dude right here, but this trapezoid, this is a base, this is a base. My height again is actually this thing that's perpendicular. This is my height. How far is it between these 2 bases? Well, that actually is just going to be 1. That actually is my change of x. Now, what is one of my bases? And it really doesn't matter which one I do here. Well, one of my bases is going to be this height right here. Again, I know you're looking at me. I'm trying to move this first height right here. And my other heights, or my other base, is this base right here. So I'll call this base 2. This one's base 1. How do I figure what that is? Well, it's whatever my y value is at 1. So if I plug 1 into x, what's 1 squared? 1. I'm going to have my first base is going to be a height of 1. It's going to be up here at 1. My second base, so base 2, well, it's at 2 is the y value. So if I plug 2 into this, what's 2 squared? That's going to be 4. If I want to find the area of this first trapezoid, and again, that should make sense. When I look at this height right here, it's up here at 4. I don't know, that kind of fits of what this looks like. But I'm just plugging these into my function because that's my y value, plugging these in. My answer is going to look like this. I'm going to have 1/2 times 5, right? So my answer is going to end up being half of 5, 2.5. So my first trapezoid, I get 2.5 units squared. Not much area. I go to my second trapezoid. Trapezoid number 2. I'll put this one in blue. Well, okay. Area of the second trapezoid. 1/2. The height. What's the height this time? Oh, hey, guess what? The height's still the same. It's still this distance between here and here, which is 1. So my height's going to be 1. One of the bases, oh, we just did it. One of the bases, we called it base 2 before. We called it this. That was what? That was this answer right here, a 4. Plus, what's my other base, though? As I go over here, what's this base going to be? Well, that's the value at 3. So if I plug 3 into this, what's 3 squared? 9. Do some fast math here. I'm going to have 1/2. Again, times 1, which is just 1/2, times 13. What's half of 13? Most days, and even on today, on this Friday, we're going to get 6.5. And I'm just going to keep going as I go here. My next trapezoid, the third one here, looks like this. And again, this is kind of annoying, but it's just simple math here. Geometry at its finest. Find the area of the third one, 1/2. The height again is going to be this distance. This is my height. Well, how far is it between 3 and 4? Well, it's going to be 1, so I have 1. One of my bases is this base, which we already did. That was at 3, so we got a value of 9. Plus my other base, this base, that's at 4. Plug 4 into our function. 4 squared is 16. So if I multiply these out, I'm going to have 1/2 times 1, which is a half, but then times 9 plus 16, 25. I'm going to end up getting 12.5. And I keep running out of room here. And I got one more to do. One more. I'm running out of colors, Mr. Royak. I guess I'll go back to green here. Green. The last one. Number 4. My fourth trapezoid. I'll put it right here. I'm going to have 1/2 times the height. Well, guess what? Height's still the same. It's that change of x, 1. And then base, the first base, this base right here. What's that base? Oh, that was at 4. So 4 squared in this function, 16. Plus the last base, my other base right here, that's going to be at 5. I plug it in the function. 5 squared is 25. I'm going to get that. So my answer here is going to be 1/2. 16 plus 25, so that'd be 35, 41. Does that look right? So 41. And I get an answer of exactly 20.5. So if I had to go back and say, what's my total area? What's the area under my curve? If I add up these 4 rectangles, my total area is going to just be adding these things up. 2.5 plus 6.5 plus 12.5 plus 20.5. So my estimated area by using 4 trapezoids, which if you look at my picture, again, I didn't draw this very well, but these things fit a little bit better than me counting squares. I think this adds up to, anybody? That's right, you guys don't talk. I'm kidding. Some of you don't talk enough. I think it adds up to be 42. And so by using 4 trapezoids, I get 42 units squared there. So if I had to compare right now and say, okay, trapezoids, only 4 of them, look how well they fit my graph, it's 42. Over here counting squares, I got 42.5. Which one do you think is a better estimate right now? I might lean towards my trapezoids, to be honest. I think they fit better having 42. But wait, as we saw with that little GeoGebra slider deal, if I could have more trapezoids, more than 4, if I could do more than that, it actually would fit better yet. So let's go more. Let's go with 8. 8's more than 4. This actually should make my answer closer to the actual answer, what it might be. So let's do the same thing for 8. Now, we could do what we just did as we subdivide this. Now, let's just talk through this, though. I still want you to do the same thing. Trapezoids, find the area. I'm going from 1 to 5, so all this is still the same area, same graph, all the same pieces here. But the one thing I want to do, though, is if I want to make 8 trapezoids, my change of x, which is really the height of this, again, is this formula, b minus a all over n. The only thing different about this is I'm still going from b is 5, a is 1, so I'm still going 5 minus 1 on top. That part doesn't change, but now n is, I don't want 4 trapezoids, I want 8 trapezoids. My change of x this time is going to be 4 over 8 or 1/2. So in a moment, this is what's going to be important here, and this is where it gets kind of crazy. As I subdivide this graph, starting at 1, going all the way over to 5, as I subdivide this, I'm going to start at 1, but then the next increment is going to be at 1.5. I'm going over a half unit. Then I'm going to be at 2. Then I'm going to go to 2.5. Then I'm going to go to 3. Then I'm going to go to 3.5. Then I'm going to go to 4. Then I'm going to go to 4.5. But I'm going to keep subdividing then to 5. But if I look at this carefully, though, this should fit, though, where this is going to be my first trapezoid, my second one, my third one, my fourth one, fifth one, sixth one, seventh one, eighth one. I end up getting 8 perfectly spaced trapezoids in this graph. And again, they're going to look something like this. I can connect the dots, connect the edges here, right? They're actually going to fit pretty darn well here. And I would argue this is going to give us an answer that's even more accurate from what we just had a moment ago. But I need to find that change of, I call it the change of x, aka that's the height of my trapezoid for this type of problem, right? Now, before we do this, we can do the same thing we did before if you want to, and just brute force this thing and use the trapezoid formula 1/2 base times height, or sorry, 1/2 height, base 1 plus base 2. Or if we want to be a little bit more streamlined, I don't know if you see this. I go back to this other one here. We can streamline this and use a little shortcut here if you're okay with this. But catch how the shortcut works though. As I looked at this first area 1, I had one base of 1, but then my other base was a length of 4. Yes. As I go to my second one, the first base was 4. Notice this is the same as this. As I go to my third one, this base was 9, but on the third one, the first base was 9. It's the same thing. We have some overlappage here. And all these overlap except for the very first one didn't overlap. And I get to the very last one, 25, that one didn't overlap either. But all these other ones, 16 shows up here, shows up here. 9 showed up there, showed up here. 4 showed up here, showed up there. They double up. The only ones that don't double up are the first base and the last base. Don't double up of times they get used in the formula. And the reason why I show you that is I call this the trapezoid rule, or sometimes the trapezoid formula. But there's a formula for you to find this, and this is what it looks like, and I'll explain here as we go. Take a moment, jot this down. And so this is how they write this. They say T. Again, T, this is the area of my trapezoids. But it's a streamline, and it looks kind of complex, right? Forgive me. But it says this is equal to the change of x. Oh, wait, we already know what that is. The change of x, that's really the height of my trapezoid. That's always the same for each trapezoid. Right, that's my h. But then what is that times? It's times half of f of a. Well, that's my first, I'm going to call this, that's the first base. That's that B1 essentially. Plus, notice it's half of that, plus the next base, whatever that is, plus the next one. You know, so base 2, base 3, whatever it is as I keep going, plus the next one, dot, dot, dot as I go. But here's what's key though, plus half of the f of b. This is the whatever my last base is of those trapezoids. So that's the last base, but I have to take half of that. And so this formula, actually I'll show you, it's a fast way to streamline this. So again, maybe pause the video, make sure everyone jot this down. This is important to have this. What this would look like, again, let's go back to the previous problem. On the previous problem, if I want 4 trapezoids, so I'm going to put a little t sub 4, so 4 trapezoids, it would say, what's my change of x? Well, my change of x, if I go back to this problem here a moment ago, what was my change of x? How far was it if I had 4 trapezoids? 1. So this is going to be 1. So my change of x is 1. Sorry, this keeps disappearing. Times. I take half of the first base. So the first base right here. Well, I'm going to go back. First base. Well, the first base is this guy right here. The first base right here is at 1. If I plug 1 in, 1 squared is 1. The first base is 1. That has a height of 1. And so my first one's going to look like this. I'm going to have half times 1 plus the next base. Well, my next base was at 2. Sorry, at 2, which when I square that ended up being 4. And then the next base was 9. And then I went to 16. And then the last base was 25. So in my formula, this is what it looks like. Again, looks like this. The first base was 1. The next base was 4. The next base was 9. The next one after that was 16. But then the very last one, I got to multiply by a half. Look at the formula because I don't have 2 of them. So I'm going to multiply by 1/2 times the last base, which was 25. Again, this is a faster way than doing 4 different rectangles one by one. It puts them together. So I have 1 times, in parentheses, I have a half. 4 plus 9 plus 16, that's going to be 29. So I have 29 of those. Half of 25 is 12.5. Help me out here, a half and a half. That's going to be 13. 13 plus 29 is going to end up being 42. I'm going to get 1 times 42 inside here. And my answer there is 42. I get the exact same answer that I got before. But this is a faster way to do it. So instead of doing each trapezoid individually, you're kind of speeding it up. So because I counted this 4 twice, I don't have to multiply by a half. Since I counted this 9 twice, I don't have to multiply by a half. The 16 twice, I don't have to multiply by a half. I just have to multiply the first base by a half, the last base by a half, and at the end, multiply by my change of x. In this case, it's just 1. Gives me my answer. So those of us that are still with me, fast forward to this. Let's streamline this. I'm going to use the shortcut here. We said the change of x, we just said this was a half by using that formula. That's important. I had to find out what that is. I'm going a half unit over, half unit over, half unit over, going down the line. My formula would look like this. Find the trapezoid, the area of 8 trapezoids, so t sub 8. It's going to say my change of x, 1/2, times. I take half of the first base. Well, the first base is this little dude right here at 1. If I plug 1 into the x squared, again, we already said this, the first base, the height of it is 1. So I have that. Plus the next base. Well, what's the next base? The next base is actually going to be at 1.5. What's 1.5 squared? It's just awkward for me. Is it awkward for you? Someone said it. I get 2.25. Again, I don't take it times a half because I'm going to have it twice. I go to the next base, which is going to be at 2. So at 2, what's 2 squared? Well, that's 4, Mr. Roy. Plus the next one. I just keep going. The next one's going to be at 2.5. 2.5 squared. 2.5 squared. That's like 25 squared. That's going to be 6.25. And I'm going to keep adding here. I'm running out of room here, so I'm going to go down below here. Plus the next one, which is going to be at 4. Or at 3. 3 squared is 9. Plus the next one, which is going to be at 3.5. 3.5 squared, 12.25. Plus the next one, which is going to be at 4. 4 squared is 16. Plus the next one, going to be at 4.5. So 4.5. 4.5 squared, 20.25. Plus the last one. Now, because it's the last one, I'm going to take half of the last one. So 1/2 times 5 squared, 25. This is going to be my formula that I'm going to end up using. So if you can take one moment, this is just a fast way to do it. I'm going to have this change of x. In this case, is 1/2. But then now if I can add up all this stuff inside of the parentheses, half of 1 is going to be a half. Half of 25 over here is going to be 12.5. So half plus 2.25 plus 4 plus 6.25 plus 9 plus 12.25 plus 16 plus 20.25 plus half of the last one, 12.5. This should add up to be 83. Check me. Maybe pause. Maybe they should check this as well. And so if I had 8 trapezoids, this is what my estimated area would be. What's half of 83? Half of 83 is 41.5 units squared. That would be my estimation having more trapezoids. As I start to compare all of this and see again now, the more I can have, the more trapezoids I can subdivide this into, it's going to fit the curve even better each and every time. So as I go back and look, I would argue again, counting squares a moment ago when we counted squares, that's pretty primitive. 42.5, that's not bad, Mr. Roy. I would argue, though, when we did 4 trapezoids, this is better yet. This is closer to the actual answer of 42. If I go even farther yet and go 8 trapezoids, this answer of 41.5, that's actually even closer yet to the actual answer. And if I could do more, right, we could do more. We could do 16 would be the next nice one to end up doing. Subdivide this into 16 pieces wouldn't be terrible. My change of x would be different, but it would fit my graph more. So my answer is probably the actual area under the curve is probably closer to 41.5 is what the actual answer ends up being of where it might be. And we could do this on and on where it might be. Now, if you want to know what the actual answer is, let's just see this, and maybe some of you want to zone me out on this. This is what you're going to do later on this year. You're going to have something like this. I want to go from 1 to 5. My function is x squared. This is actually going to be the exact answer. They're going to ask us to antiderive this, and this is the antiderivative of this. I'm going to plug in 5. I'm going to plug in 1. And so this is what it's going to say. I'm going to have 1/3, plug this 5 in, 5 to the 3rd power, minus 1/3, plug 1 in, 1 to the 3rd power. 5 to the 3rd power is 125 over 3. 1 to the 3rd power is 1. My answer is going to end up being 124 over 3 is what my answer is going to be. And again, 124 over 3, Mr. Roy. The exact answer, the exact area under my curve, this is exactly 41 1/3 units squared is what the exact answer is going to be for this problem. We're going to use definite integrals, and that's what it's going to be in a moment. But are we close here? Yeah. This is way closer than this one was, and way closer than what this was to what the actual answer is. Does that make sense? Hope so. Again, don't worry about this. I'm not going to ask you to do this. You don't know how to antiderive, and but that is the exact answer, though. The exact answer is 41 1/3 units squared is the exact area under the curve. I just added up an infinite number of rectangles, but I really didn't. Anyway, we'll talk about that later. Last thing, and I'll be done. I know some of you are ready to be done right now. But last thing, here's a different kind of question here. I have an airplane. An airplane measures how fast it goes, but wants to figure out how far it has traveled. The velocity is measured every 15 minutes, is recorded on the table. Using the trapezoid rule, so that formula I just showed you, can you estimate the distance the plane has traveled between 6 a.m. and 7:45 p.m.? I'm going to argue with you this is going to be faster than what we just did in looking at that problem before. I want to estimate the distance. We talked yesterday about this. If I were to make a little graph, and this is kind of what this graph is saying, if I'm starting at, let's say this is 6 o'clock right here, every 15 minutes, things are changing, right? My velocity is changing every 15 minutes is what this is saying. At first, I'm going 150 miles per hour the first time. Then I'm going at this, I'm going 120. And then I'm going up to 170. And then I'm going down to back to 150. And again, I can keep putting dots here. But in a moment, what I want to do, if I want to find the distance, that really is the area under my curve. And again, I really don't have a curve here, but what I actually have, if I connect the dots here, and again, I'm just doing the first few of these. If I connect the dots, do you see what I'm actually making right here? I actually have, right now, 3 trapezoids. And And again, I could keep going and go to 7 o'clock, and 7 o'clock, how fast is it going at 7 o'clock? It's going 140, so 140 is going to be like, a little bit lower right here, and play connect the dots there too if you want to play connect the dots. And I have another trapezoid. But the area under my curve actually is the distance, and the reason why it's the distance is because these labels right here are miles per hour. That's my velocity. This right here is my time. And my time right here, I might argue if we measure it in hours, and we're actually measuring this every 15 minutes, which is every quarter of an hour, area under a curve is just my base, hours, times my height, which is miles per hour. And what ends up happening is these things cancel out, and I'm just left with miles. So the area under my curve is just again, the distance I travel as I go across here. So conceptually, even though you see this right here, we can streamline this. I just need to find the area. And if I use trapezoids, this is what I would do. I go back to that formula. Mr. Royk, what's the formula? The formula is right here. Oops, right here. See it? It's there, right? Go back to that formula. This is my trap rule. I need to find what's my change of x. Well, on this question, what's my change of x? How far is it changing from 6 to 6:15? And from 6:15 to 6:30, this is my change of x, what that increment is. And what is that change? It's 15 minutes, Mr. Royk. I would argue, though, because this is in miles per hour, I would argue 15 minutes is the same thing as 0.25 hours. So I would argue that my change of x is going to be 0.25. It's a quarter of an hour. Then it says take half of the first base. Well, I have half. What's the first base? Well, what is this first distance, this first base right here? Call that base 1 right here. Well, they tell me it. Right here on the table, it's 150. Then I add the next base. Well, what's the next base? That's at 6:15. That's 120. They did all the work for me already. I don't have to plug anything in. Plus the next one. What's the next one? Well, that's at this one right here, which is 170. And I'm just going to continue on. I'm going to erase this for us. I'm going to continue on. So plus 170, plus the next one, which is 150, plus the next one, which is 140. And I'm going to keep going, 80, 130. And then the last one is 150. I have to take half of the last one. So that's, again, using that rule, half of the first, half of the last, and add these up. And if I do this correctly, this is what I should get. I should get 0.25, because that's my change of x, 15 minutes, or a quarter of an hour. But if I add up these things, half of the last one, half of 150, 75, I think I get an answer of, I don't know, did I do this? Sorry. I did this at one time. I think you should add all these up. Try it. We should get 940, what it is. So what's 0.25 of 940? I'm finding my distance to end up being, which is the area under my curve, my distance to be roughly 235 miles. Again, why is it miles? Because I'm multiplying my y's times my x's. That's how I find area. I'm multiplying miles per hour times my time, and my time is 0.25 of an hour. So if I take miles per hour times 0.25 or times hours, they're going to cancel. I'm just going to be left with miles, and that is a distance. So finding the area under a curve for a velocity versus time graph will always tell you the distance you travel. But you see how easy this is to use? You can just use those miles per hour as my bases, because that's what they are if you were to draw the graph of them. Some of you maybe I lost on this journey. We'll pick it up on Monday. Some of you maybe this makes sense, and maybe you like this. When I come back on Monday, we can talk about this too. There's a program on your calculator I can get for you to upload these on here, but I'm not going to worry about that here. Here's what I'd like you to do. The rest of the time, I want you to try these questions. They're not horrible. There's not that many of them either on this worksheet. Help each other out. See if you can get the right answers. If they say use 4 trapezoids, use 4 trapezoids. If they say use 6 trapezoids, use 6 trapezoids. If they say use 8, use 8. So listen to what they have and how they want you to subdivide these of where they are. We'll go through this and talk about it on Monday, but help each other, work together. Again, we're not doing this alone. We're doing this together. And you have people around you, so let's keep growing. Thank you for your work. Have an awesome day. Have an awesome weekend. Bye.